Good morning, everyone. It's very good morning. Shall we begin the session? Today's topic is logical operations in C. That is, what are the various logical operations that is performed in C language? So this is the part of manipulating the information. All right. So let's start with the first one. That is, what are the various logical operators in C? That includes the AND, or not. AND means if one of the input is true, then the output is true. Or is when one of the input is true, output is true. And is both the inputs are true, then only the output is true. Not is negation, that means reverse of the input. For example, if I give 0, that becomes 1. Negation, if I give 1, that becomes 0. Now, observe that a bitwise operation will have a behavior that is meaningful behavior matching its logical counterpart in the special cases in which the arguments belong to this or arguments belong to the other. So when we use the AND or NOT, they are known as the logical operators, and that is used with a logical operator that do not evaluate their second argument if the result of the expression can be determined by the evaluation. For example, when the evaluation says A and B, then will never cause division by 0, and the expression P and P++ that will be dereferencing of a null pointer. Next is shift operation in C. How to use a shift operation that provides a set of the shift operation for shifting the bit pattern to the left to the right, and for an operand X having the bit representation with the 0, that is X is shifted to the XK bits to the left, dropping off the K most significant bits and filling the right end with the K zeros. And the shift amount should be a value between 0 and n-1 so that it is used with the X right operand j, then right operand k. That is equivalent to xjk. That is corresponding with logical operators, arithmetic operator. That means we are using both arithmetic operators as well as a logical operator in this. And when we use arithmetic right shift, that fills the left end with the k, repetition of the most significant bit, that gives a result with xn-1, xn-1, n-1, n-2, xk. And we are using the effect of applying the different shift operations to some simple 8-bit data that is used for this. This is the operation argument x 011 00011. This is 100011. Then x4 modulus 4. This is 0011 0000. Then this is x logical more than 4. Then x logical more than 4. This is used for the shifting right arithmetic operators. And the C standard do not precisely define what kind of or which kind of right shift should be used. And for the unsigned shift, there is a right shift that must be a logical shift, either by the arithmetic or the logical shift that may be a use, that may be unfortunately that will use in practice with the problems with the machine instructions. Now this is one of the table that shows how to represent with the hexadecimal, binary, hexadecimal logical, that includes the binary as well as hexadecimal, arithmetic, binary as well as the hexadecimal. Next is integer representation that we have done, that is also included with the C data type, integer data type, that is included with the 32-bit machine, and that is used with the square brackets. Then integral data type, this is integer that includes 2 bytes. So one of the method that includes 2 bytes, and the float takes 4 bytes automatically. Now these are the various data types that have a different range. When we talk about the char, this takes 1 byte, and the minimum range is -127 and the maximum range is 127. This is so in the assignment, or if a question arises, what is the range of the char? Only char, not the unsigned char. So your answer is -127 to +127. If I'm talking about the unsigned char, this is from 0 to 255. Then short int, this is -32767 to 32767. Unsigned short 0265535. Again it is int. Again it is unsigned int. Then there is a long integers. Then there is an unsigned long. Then long. Then unsigned long int. So this is also used with the unsigned long int. Now, this is the guaranteed ranges for the C integral value that is available with the C language. Now this is the negation. This is the unsigned number that is used with the C language that we are using. By default, it is used with the unsigned number. Example, for W equals to 4, when bit I in the binary representation has a value 1, it contributes to I to the value. That means it contributes with the unsigned interpretation that we express with the interpretation as a function B to U, that is binary to unsigned. Now next is a 2's complement encoding that is used. So when I use 2's complement encoding, that is used with the sign weight, that is -2 part W minus 1. That is a representation value is negative and it is set to 0 when the value is non-negative. Now next one is the important number that is used with the both numeric values as well as the hexadecimal values. Now this symmetry arises because half of the bits pattern represents a negative number while half represents a positive number or the non-negative number. Now this is the exact side integer values that is used by the Java with various data type range. This is 12345 minus 12345 53191. This is done. We have done already in the last class. Now the next part is signed versus unsigned. As I told you, there are multiple data type, each having of the types int or each having of the type signed as well as unsigned in the C language. Now, alternately, they can also happen implicitly when an expression of the one type is assigned to the variable of the another, as in the following code. This is int tx ty unsigned ux uy. This is tx equals to ux, uy equals to ty. This is cast to the signed, this is cast to the unsigned. And when printing numeric values with the printf, the directives %d u X are used to print a number as a signed decimal, unsigned decimal, or in hexadecimal format respectively, and we are using the printf that does not make any use of any data type information, and it is also possible to print a value of the type int with directive %u and a value of the type unsigned with the directive %d. So it is used with the u as well as with the d. For example, this is one of the example, int x equals to -1, unsigned u equals to 21478. This is 2 to the 31st. This is available with this. Then printf x equals to %u, %d, xx, then this is u equals to u, %d, uu. So this is when you run on a 32-bit machine, it prints the following. This is 42946 minus 1, this is 21478, this one. In both the cases, printf prints the first as it represents an unsigned number and second as it's represented a signed number. And we can see the conversion routine in action, that is T to U, U max 32, 2 power 32 minus 1. This is used with the 2 power 32 or 31. And some of the behavior arises due to the C handling of the expressions containing combination of the signed as well as the unsigned quantities. Now next is expanding the bit representation of a number. So one common operation is to convert between the integer having the different word sizes while retaining the number or same numeric value, and this will be used if possible when the destination data type is too small to represent the desired value. So converting from a smallest to the largest data type, however, that should also be possible, will be used in the data type that is possible for the representation of the numbers. This is the next one that you run on the 32 bits indent machine that is using the 2 complements numbers with a 16-bit integer. This is the example of the sign extension that is work with the short sx or the unsigned uy. Then next in truncating the element, that is also truncate, that means reduce the number of the bits representing a number. Now next part is truncating a number, that means reducing the number of the bits representing a number. Yeah, this is same as a round off function. This is one of the example that is used to truncate a 4-bit value. Now this is one of the example. That is how to truncate different values in one series. This is the integer addition with the 4-bit word size. Then the sum could appear or could require the 5 bits. This is the 2's complement addition. We are first of all we have to find out the 2's complement. That means first of all we have to find out the 1 complement, that is reverse of the ones and the zeros. Then make the addition of the 1 to the 1's complement. This becomes 2's complement addition. Now this is the relationship between the integer and the 2's complement addition. Now integer arithmetic with the 2's complement addition examples. This is fill in the following table with the style of this. Give the integer values of the 5-bit argument, the values of both their integer and the 2's complement sums, the bit level representation of the 2's complement sum, and the case from the derivation of the equation 2.14. So this is used with the impetent with your analysis of the overflow conditions for 2's complement addition, and also present you with the following implementation. Now, one is a addition, one is a negation, that means reverse. This is the hexadecimal, decimal, hexadecimal. So one is a 2's complement multiplication. This is used with x into y, u into t, x into y, 2 power t. Now this is a 3-bit unsigned and the 2's complement multiplication example that is used with the bit level representation of the full product that may differ, that although the truncated products are also identical. Now this is dividing by powers of 2. Dividing by powers of 2 can also be performed using the shift operation but we use a right shift rather than the left shift, and the two different shifts, that's the logical and the arithmetic, also serves this purpose for unsigned and the 2's complement number, that is respectively it is used with the one of the integer values. This is applying the arithmetic right shift. Then next is how to apply the right shift with the 2's complement addition. This is one of the example that says hash define m, hash define n, int arithmetic or the arith, int x into y, int result equals to 0, then result equals to x into m plus y n. Then return the result. This is used with the int arithmetic, int x into y, int x t equals to x, x is right shift 5, then x minus equals to t. If y is greater than 0, then y plus equals to 7, that is y is right shifted by 3. Then the final thoughts on the integer arithmetic, that is used with the foo, that is used with the bar. This is x equals to foo, y equals to bar. Next is fractional binary addition, fraction binary number, that is representing with the fractional binary segmentation with the digit to the left of the binary points. This is IEEE, floating point notation. There is an exponent part, there is a mantissa part. Single precision, normalized, denormalized. Now these are the examples of the non-negative floating point number. This is represented with the smallest positive normalized value that have a bit representation with the 1 in the least significant bit. Then floating point operation, that is used with the IEEE with the round functions operation, that is used over the real numbers, computation of the real operation. And the compiler might be tempted to say one floating point addition by generating the following code. This is t equals to b plus c, x equals to a plus t, y equals to t plus d. Now this is one of the example that is used with the variable xfd. X is representing the int, f representing the float, and d is representing the double, that is used with the minus infinity to the plus infinity. Now this is a summary of this, that is a computer encode information as bits. That means it can represent the information as a bits, bytes, kilobytes, megabytes, whatever the representation that we want. with underlying the bit pattern that does not change, and on a 2's complement machine, this behavior is also characterized by the T2U and the U2T, with a multiplying with the power of 2 with the power of 1. This is a homework assignment, so the problem that is available with this, then B level or the bit level integer coding rules. This is a code to implement the following functions. These are the various examples. Sorry, these are the various solutions of this exam. So in the next class, that is in the tomorrow's class, I'm going to take with this, that is chapter number 3. What are the machine level representation of the programs, or how we can represent with the machine level program or the machine level representations. So till now, till chapter number 2, any doubts anyone? So if there's any